Welcome to FEA Insight and FEA Academy YouTube channel. Master Finite Element Analysis with our comprehensive series of videos tailored to both beginners and experienced engineers. Explore fundamental concepts, advanced techniques, and real-world applications through case studies and practical tips. Stay updated with the latest developments in FEA, empowering you to excel in your engineering career. Hello everyone, welcome to this episode of FEA Insight. Today I'm going to present you what is finite element analysis. Let's start with the agenda. First, I want to present you the methods for solving an engineering problem and the different numerical methods. I want to do also an introduction to partial differential equations. Don't worry, I won't go into the mathematical details, but just the fundamentals. And finally, I'm going to answer the question, what is FEA? First, let's start with the definition. According to NAFEMS, the International Association for the Engineering Modeling, Analysis and Simulation Community, engineering simulation is the use of numerical, physical, or logical models of systems and scientific problems in predicting their response to different physical conditions. So there are three methods available to engineers for solving problems. First, we have the classical methods, then the numerical methods, and the experimental methods. Let's see them in detail. First, the classical methods. The classical methods are based on closed-form solutions, and in some cases, these methods give very accurate results. You have to know that in structural analysis, stress analysis are based on equations of the classical methods, such as the strength of materials and the famous theory of elasticity. However, they are only applicable to very simple problems. For example, a cantilever beam, a simply supported plate, torsion of a simple section, for example. Even if they have been used intensively at the beginning of the 20th century, they are only used for structural problems with simple geometry and loading and boundary conditions. It cannot be complex. So the weakness of such methods is that as an engineer, you must make many reductive assumptions to render complex situations compatible with the equations framework. You know that the real-world problems involve cases with complex shapes, boundary conditions, and material behaviors. These real cases cannot be solved using the classical analytical closed-form solution or methods. So, numerical methods have been developed to solve the more complex problems. So on the other hand, by making assumptions, you can use the numerical methods to produce mathematical representation of real-life engineering simulations to solve complex problems. With the advent of powerful computers, the numerical methods have proven to be increasingly accurate and reliable in solving complex problems. They are approximate, but the assumptions on which they are based are less reductive than those of the classical methods. In other words, the assumptions of the numerical methods are closer to the reality than those of the classical methods. Finally, we have the experimental methods. They are based on measurement performed on a physical prototype, and they are time-consuming and expensive. Moreover, to obtain accurate results, several specimens must be tested. However, this method is useful for validating the numerical models. To summarize, let's compare the classical methods with the numerical methods. So here on this table, you see we have the classical methods and the numerical methods. For the equations, classical methods and numerical methods are exact. For the solutions, the classical methods are exact, while the numerical methods are approximate. In terms of number of solutions, the classical methods is very reduced because it is only valid for a few standard cases, the simple cases. For the numerical methods, all the problems can be solved. For shapes, boundary conditions, and loading, we have to do some simplifying assumptions for the classical methods, to apply the classical methods, I should say. Okay? While for the numerical methods, there are no assumptions. Shapes, boundary conditions, and loading are treated as they are in the reality. And finally, for the material, the classical methods are limited only to isotropic and only one material. On the other hand, the numerical methods can use all types of properties with an unlimited number of materials. Here, I want to present the advantages and disadvantages of prototyping. First, the advantages, okay? They are reliable, they are well mastered, it makes long times we are doing prototyping, and it is trusted by the regulatory agencies. Also, you have to know that prototyping is essential for calibration and correlation of your simulations. For the disadvantages, they are very expensive compared to finite element analysis, and they are time consuming. It takes a lot of time to build a specimen, to build a jig for doing the test. Also, it degrades the competitiveness of the products by raising design cost. The data integrity also are more difficult to maintain compared to FEA. And finally, they cannot replicate all conditions. Okay, we have a lot of limitations with prototyping. So let's dig in detail into the different numerical methods. The 4 numerical methods most commonly used to solve the engineering problems are the finite element method, the boundary element method, the finite volume method, and the finite difference method. All these methods can be used to solve the same problem. However, substantial differences exist among the methods with respect to result accuracy, ease of programming, and computation time. When internal details are required, such as the stresses in a part, for example, the boundary element method gives poor results, as it only considers the outer boundaries. In this case, methods like finite element method, finite volume method, and finite different methods are preferred. The finite volume method, can be used to solve stress problems, but it is preferably used to solve the CFD problem, the computational fluid dynamic problems. The FDA method, the finite difference method, has limitations when it is used with complicated geometry, assembly of different material components, and the combinations of various types of elements, the famous 1D, 2D, and 3D elements. So, to solve complex mechanical problems, the finite element method is by far the best method in terms of accuracy and computation time. But these methods share a common point. They approximate the solution to the partial differential equations that govern physics. Here, I want to do a quick reminder about the partial differential equation. A differential equation is a mathematical equation that relates some function and its derivatives. Differential equations are used in many fields of science and engineering. They make it possible to link functions representing physical quantities and their derivatives. These derivatives represent the rates of variation of these functions. Okay? So from a mathematical point of view, a PDE can be used to formulate phenomena described by functions with several variables. In such a case, the equation will be made up of multivariable functions and their partial derivatives. A partial derivative of a function of several variables is its derivative with respect to one of those variables with the other L constant. However, only the simplest differential equations are solvable by mathematical expressions that can be evaluated in a finite number of operations, also known as the closed form expressions. While all physical problems can be expressed mathematically as differential equations, not all the differential equations can be solved analytically. Many differential equations do not have closed form solutions. But it is possible to find solutions to a given differential equation without determining its exact form, the famous closed form solution. Indeed, if a closed form solution is not available, the solution can be numerically approximated using computers. It is why numerical methods have been developed to define solutions with a certain degree of accuracy. So here, let's talk about the need for analysis. When we have a real structure, we know that it is characterized by the geometry, the materials, the properties, the boundary conditions of the real structure. On this real structure, we can apply excitations. By excitations, I mean forces, pressure, acceleration, thermal effect, vibrations, etc. And from that, what we want the displacements, the forces, the stresses, the strains, the natural frequency, etc. applied, resulting on the real structure, I should say. So the need for analysis comes from the fact that the FEA analyst must define the structure's response under given excitations in order to ensure that the structure can sustain the excitations. So it gives us the need for modeling, okay? In structural analysis, the domain of interest is solid mechanics. The field variables are the displacement, the dependent variables, and they are governed by differential equations. And we have the boundary condition, which are the specified values of the displacements, the field variables, at the limits of the analyzed system. So the continuum nature of the problem and of the governing equations means that the real structure cannot be analyzed as is. Only a model of the structure can be analyzed by a computer. The FEA analyst requires a tool with which to model the structure and analyze the model. So, during this process, the continuum problem is transformed into a discretized solution using the finite element method, a numerical process for solving the partial differential equations associated with the field problems. So the classical analysis is describe the real structure and is governed by partial differential equations that the computer cannot solve. By doing discretization, doing assumptions, applying equilibrium, the stress-strain law, and some compatibility displacement, we can transform the real structure into a structural model. And this structural model is governed by matrix equations. The transformation from PDE to matrix equations has been done using the finite element method. So we obtain a matrix equation that the computer can solve. So in solid mechanics, the finite element method is based on this matrix equation, which defines the state of equilibrium of forces acting on the structure. So this general equilibrium equation, okay, in this one we have the mass matrix of the system, the damping matrix of the system, and the stiffness matrix of the system. And we have three vectors: the acceleration vector, the velocity vector, and the displacement vector. Everything is in this relation with the different metrics. Equal what? The excitation. Here we have the vector of the excitations, the forces, the pressure, the temperature, many types of excitations. This general equilibrium equation can be derived for different types of analysis. For static analysis, for buckling analysis, for vibration analysis, or for transient and frequency response analysis, the dynamic analysis. While you may not be able to define how a complex structural piece will behave, you can do so for a simple part of it. So FEA is based on the following idea: divide and conquer. If you divide a structure into multiple elements, the behavior of an individual element will provide a good approximation of local behaviors. For example, displacement, stress, strain, etc. So to be able to make simulations, a mesh consisting of up to millions of small elements that together form the shape of the structure is created. We call that the discretization or meshing. Then the calculations are made for every single element. And combining the individual results gives us the final behavior of the structure or the system we want to analyze. It means that we obtain the results at certain points within the structure, but not at every point. These certain points are called nodal points and are located at the boundaries of the elements. The accuracy with which the variable changes across the elements is expressed by interpolation over the elements using polynomials, linear, quadratic, cubic, etc. So the global assembly of the individual elements will reflect the behavior of the actual structure, the actual system. So it means that if you assemble enough of these simple pieces, the elements, you can define how a complex structural piece will behave. A good discretization is a matter of balance. The more elements you use to represent your structure, the more precise and realistic the response you will get. But be careful, because nothing is free. The more elements you will use to represent your structure, and the greater the calculation time to solve it. So in summary, the key term here is discretization. Discretization permits to transform a continuum problem into a discretized solution. So the continuous problem, the continuous system, is the reality, okay? It is defined by an infinite number of points, an infinite number of equations. And the discrete system, which is the model, is defined by a finite number of nodes and a finite number of equations. So here are examples of discretizations. Here it is a simple plate with a hole in tension. Here we use a 2D discretization. Another example of a fitting discretized with solid elements. Here it is a detail of this fitting. Here, this is an example of model for a complete aircraft. Such FEM is named Global Finite Element Model and is used to capture global structural behaviors. The picture is here shows you the global finite element model of the aircraft with the skin removed to show you the internal structure and all the details of the model. You can see a lot of details that can be included in such model. Finite element analysis is based on the following 4 key points. The elements, and what is an element? It's a small section of the analyzed part, okay? So each section is called an element, and it is the result of the discretization of the machine. Each element acts on its neighboring element. FEA assembles the equations from all the elements into one large matrix equation. And the numerical solution is defined by a computer by solving this large matrix equation. Then we have the second key point is the governing equations. The governing equations define how each element behaves. The FEA solver is going to compute these equations for the analyzed physical part depending on how it is held and loaded. The key concept of FEA is that if the elements are small enough and are spread intelligently across the part, the numerical solution can closely approximate reality. Okay? So the more elements you have, more accurate is the solution. The third key point is finite. Okay? It represents the countable number of elements used to represent the structure. The elements are of finite and measurable size. And finally, we have analysis. The part analyzed under certain conditions. And you have access to a wider range of analysis with the FEA. You can do some static analysis, dynamic analysis, model analysis, buckling analysis, linear and nonlinear, etc. So if you want to learn more about FEA, feel free to contact me via email or on LinkedIn, and see you for another episode of FEA Insight.